this back into the flow of things. So we're talking about synchronous machines. We're in chapter 9, and we are slowly going through the electromagnetic end of things, modeling. And we are really broken up into two different pieces, right? When we talk about the electromagnetics within the synchronous machine, there's the interaction of the armature windings with one another, right? How IB, or how phase B affects phase A, how phase C affects phase A, vice versa, all run in a circle. And then we have the effect of the field winding, okay, which is on the rotor, on the stator. And both of those together are going to have an effect on the induced EMF at the terminals of the machine. And that is the generated voltage that we're actually worried about, that will be, exciting current that will flow out to the rest of the system and everything that's out there. And so where we left off was at section 9.3.2, which is the induced EMF due to the armature reaction. And one additional reminder, today I'm also going to assign homework. So there'll be two things that I'm going to be sending out to you. I'm just writing myself a reminder to do that. I'll be sending out the project as well as the homework. So, section 9.3.2, the induced EMF due to the armature reaction. So this, again, is the effect of the stator windings on one another. And what we saw was that we can combine the three together into a single equivalent self-inductance. So without going through all the math again, right, we have three different relationships if we're talking about the armature reaction. We have phase A's self-inductance. We have the mutual inductance between phase A and phase B, and the mutual inductance between phase A and phase C that we have to worry about. Now we can represent the three of those as three individual equations, okay? However, we can also combine the three together if we assume that we have balanced operation, okay, where the magnitudes of IA, IB, and IC are all the same, as well as magnitudes of the magnetic fields, and there's no unusual distortion or problem with the shape of the generator itself, and combine them into a single equation, which is 9.6, which is the armature reaction represented as the magnetic field. K2, which is a constant we'll talk a little bit more about later. IA, this is the magnitude of the stator current. E, J to the synchronous frequency, which is the rotational frequency of the machine. T, because this is an instantaneous value, minus theta, which represents the phase shift. So equation 9.6, right, tells us that we can represent all mutual inductances as a single equivalent self-inductance. Now moving on from there. Okay, and before I start a new set of notes, there's one little last piece here. And so we can represent this as an induced EMF because, right, this is not a voltage. if you go back up to the section title, our goal was to find the induced EMF. And so the expression for the, what we're going to call E armature on phase A, this will be the induced EMF due to the armature reaction, is equal to this. Negative J times K3, which is going to be a different constant than K2. Times the value of the armature equivalent magnetic field intensity at time equals 0. And the reason why we use it at time equals 0 because that's going to be your maximum value. That will also be represented as this right here. So what you can see is that we can represent, or we can group a lot of these terms into a value that we will call the magnetizing inductance. Or reactance, because we're using the value of x instead of x. Now, what is our goal here in this chapter? Because I know the middle of this chapter can be a little bit, I don't know what the right word would be. You, to a certain point, sort of lose track of what it is exactly that we're trying to do. Like, okay. We started out with stuff that made sense, talking about electromagnetism and the relationship, between current and flux density and induced EMF. And then now we're in the middle and we're talking about armature reaction, field reaction, but what's the end goal? So the end goal is to come up with a model of the generator that looks like a circuit. Okay, we want to have one where there's an internal EMF, we have a magnetizing reactance, a leakage reactance, and all different pieces that can correspond to the physical parameters of the generator itself. So for example, the magnetizing reactance will be part of this circuit that we're going to draw. But we can also relate it back to different values that are physical representations of what's going on inside the machine. So that's what we're working towards. We're splitting this up into two or multiple different pieces. We're coming up with the equations that represent them, hopefully ones that are in terms of currents and reactances. Okay, and then at the end, we're going to present a circuit which now we can connect that to a larger system. Okay. So, and the good thing is that's the next thing that we're going to talk about, which is the circuit model for the combined EMF. Okay, so this is section 9.3.3. Circuit model for combined EMFs. So we can represent the phase A armature behavior using the equivalent figure that we're going to show right here. So this figure represents phase A armature behavior. So what we have and we'll go back and explain each piece along the way. We have an internal voltage, which we're going to call EAF. Okay? In series with a value that's XM. Okay, right? We just defined what that value was. That's our magnetizing reactance. That's also going to be in series with another reactance value, which is going to be XL. That's going to be our leakage reactance. And then we're also going to have a series internal resistance, which is, we haven't really discussed that value. That's just going to be the resistance of the coils of the winding itself. Right? When we have this generator running, the stator windings, the armature windings, they have an internal resistance, right? They're not assumed to be zero resistance. Okay, so this, right, magnetizing this right here is our leakage. This is our winding resistance. And then what we have is the actual terminal voltage of the generator itself. So VA of T, or I can just write it as a vector. And that's the actual terminal voltage. And this right here, this induced EMF, it represents the linkage, or the linkage between the rotor and the stator. Now, I'd like to, for a second, just go back and figure out where all these values came from previously in the notes. Well, this one is fresh in our mind. This is equation 9.7, right? We had just got done talking about that. So this right here, I'm running out of space. A lot of arrows. Okay, so this represents the armature reaction as described by equation 9.7. Okay, now let's go back into the notes for 1 second and see where the other pieces came from. It's been a while since we did this. So we talked about so section 9.3.2 talked about the induced EMF due to the armature reaction, which really we're just going to be representing as that magnetizing inductance. So it's a voltage drop along the series element. The section 9.3.1 talked about the induced EMF due to the flux linkage with the field winding, And so that was equation 9.1. Okay, so if we go back to our notes here. So this comes and then the internal resistance of the stator windings, we didn't really, I mean, that's something we all understand. Okay, so now what we have is equation 9.9 and equation 9.10. And this is just going to use good old KVL in order to describe two different values. So we have the terminal voltage. We also have this value we call EA, which is the internal voltage of the generator. And then we have EAF, which is the linkage between the rotor and the stator. It's a little bit confusing. So EA encompasses essentially the armature and the field reactions together. This is the linkage between the rotor and the stator. This is the linkage between the armature windings, or with one another. Sum the two of those together, you get EA. Then, when we take into account the lossy parts of the generator, which is the leakage reactance, right? That represents the field, the magnetic field lines that are not that don't connect any two of the windings, whether that's the rotor and the stator or the two of the stator windings, as well as the loss associated with the resistance. We all know I squared R and what that means, right? So the internal voltage, and this, right, you could write yourself very easily. Again, hopefully you're all very good at KVL by now. EA is equal to EAF minus JXMIA, right? The voltage drop across XM relates EA to EAF. And then lastly, or not lastly, but next, VA, which is the terminal voltage, is equal to EA minus JXLIA minus RS times IA. And this value right here, we're going to call that ELS. And I can just leave it as EL. And then there's a third version of this where we could say that VA is equal to EAF minus JXM plus XL times IA minus RSIA. Let's just combine the two equations together. And the reason why this equation is important is because it defines a value that we're going to use over and over again called the synchronous reactance. And that's going to be represented as XS. So what we're going to do is combine those two together into a single value when appropriate. Okay, so this, if you're trying to understand this chapter, I think this is actually a good point to start from, almost. Okay, and there's two ways of looking at this chapter. You can start from the beginning and move forward, which is the way that makes more sense to present it initially, because we don't want to start off by showing you values that you don't know what they mean. But in another respect, if you're trying to understand this, working backwards from here also makes sense, because this is the way that we model the way that the generator works. You can split it up into its individual components. Now we know what those individual components represent physically. Okay, this is a model that we can integrate into a larger system. And then you can move backwards and say, okay, well, if I'm given this x, y, z values, I can calculate the value of EAF. If I'm given x, y, z values, I can calculate the magnetizing reactance. If I was given x, y, z values, I can calculate the leakage reactance. And let's say the internal resistance of the stator windings. So this figure, in combination with equations 9.9 and 9.10, I think really does tie together a lot of stuff in this chapter. That being said, also, this is the basis of a lot of the homework problems, which will be assigned today, and any potential quiz problems that you might have. Most of them are going to be based off of using this circuit model and implementing that as part of a larger circuit, or simply just defining it based on the physical quantities that I'm given to you. So hopefully that picture makes this chapter seem a lot more practical with application. If you actually see, okay, now this can be used for something. Okay, the next section, and the good thing about this is, the first three sections of this chapter are really, really dry. Not the whole class, I'm sure this is not as fun as some other stuff, but really, really dry, trying to get to that point. But now we can do, I think, the more interesting part, which is taking this circuit and seeing how it reacts in certain other conditions. We can look at short circuit conditions, open circuit conditions, and this will give us some insight into the way that a synchronous machine reacts to certain external stimuli. Okay, so section 9.4 talks about power output, stability, and loss of synchronism. So, although this title may not clearly state it, we're going to be talking about blackouts here. Okay, this is the beginning of the blackout. 99% of the time is an event that causes a synchronous machine or generator to begin to lose stability, which means it'll start speeding up or slowing down, moving away from the 60 hertz expected rotational frequency. And then that instability is going to cause loss of synchronization between multiple generators. And once that happens, essentially all the voltage magnitudes will begin to drop, which will then only further cause this problem to go out of control. Okay, so induced EMFs in the stator windings cause several different things. Obviously, they cause the line currents to flow. Sort of a no-brainer there, right? You apply a voltage to some sort of a system, including a load. If it's a closed circuit, then there'll be some current that flow along the lines. It also produces electromechanical torque, which opposes that which is supplied mechanically. And I'll explain what that means. So, in a synchronous machine or generator, right, we have mechanical power or mechanical torque that's coming in. Okay, let's, for the sake of argument, let's just say we're turning it with our hand. It's going to be some sort of a turn in reality, but right, let's say we're turning it with our hand. Okay, if we apply an increasing amount of torque, what's going to end up happening is that if there's nothing connected to it, so let's say very low friction, there's no load, and this is just a wheel, okay, that is very easy to turn. It's going to keep speeding up and speeding up and speeding up the more torque that I apply to it, okay? So what causes the synchronous machine to reach stability at the 60 hertz is that the induced EMF, right, and we saw this a little bit in one of the pictures. No, I can't. The induced EMF causes essentially an electromechanical torque that opposes the mechanical torque that you're applying, and that acts, so the electrical load that may be, you know, some washing machine that's plugged in 100 miles away, okay, that draws current, which is then transformed inside of the synchronous machine to an electromechanical torque, which opposes the mechanical torque that you're putting in. And so those two torques equal one another, which what that does is it causes the rotational frequency to stay the same. So what we have is an electrical torque and a mechanical torque, which equal one another. Okay, if they don't, then the machine is going to begin to speed up, meaning if the load is too low, there's less electromechanical torque than there is mechanical torque. Okay, then the thing will begin to speed up. If there's too much load and there's not enough mechanical torque coming in, then it'll begin to slow down. It's sort of like, yeah, go ahead.
So it's either they equal or you have instability, right?
Well, so instability, I would say denotes, so you can have an unstable equilibrium, and you can have a semi-stable equilibrium, and you can have a stable equilibrium, right? So it's sort of like you can have this point, if you deviate a little bit from it, a stable equilibrium moves back. So you can leave the equilibrium value and come back to it.
So if you attach a greater load to the synchronous machine, then it's going to have to speed up and accommodate.
And then eventually come back to 60. So you can have small changes. Normally, the well of stability is small, okay? So we're not going to have the frequency, we're not going to have frequency go from 60 hertz to 100 hertz and then eventually return to 60. But to accommodate changes in load, it may go from 60 to 60.2 or 60.3, reach the new equilibrium value, and then return back to 60. So, yes?
You said if the mechanical torque is too low, it slows down. If the electric is too high speeds up.
So essentially it's this, sometimes when I say things like that, I mix up the word because I forget where I started the sentence. Okay. Mechanical torque, electrical torque. Okay, this is the input, this is the output. If you have too much input, too little output, what's going to happen is that the thing is going to begin to speed up. If you flip it, too little input, too little mechanical torque, too much output, too much electrical torque, the thing is going to begin to slow down. The analogy that I was about to use was the rowing machine. Has anyone ever used a rowing machine like the gym or something like that? There's that resistance value that you can turn up and down. So you're doing the rowing machine, you have a nice rhythm going, whatever certain number of strokes per second or minute, and then someone turns the resistance down, you're going to begin to speed up because it's easier for you to do what you're doing. They put it back, you'll go back to your whatever certain number of strokes per minute, then they flip the resistance all the way up, you're going to slow down because it's going to become a lot harder for you to do what you were doing. So that's an analogy I think that nicely reflects what's going on here with the tau E and the tau M. Okay, so there you go. That's the reason why I like to write things down, because sometimes when you talk TE, TM, and it all gets okay, so that's when the machine speeds up, that's when the machine slows down. And like I said before, just because it speeds up or slows down, it doesn't necessarily mean we've lost stability, okay? It just means that we're migrating to a new equilibrium value. Because what'll happen inside of the machine, potentially, is, let's say it's this case right here. This case. We have a little bit more load. The machine will slow down for a fraction of a second or a couple seconds or so. The control algorithm within the generator will increase the amount of fuel being supplied to the turbine or whatever the mechanism is there, which will then increase the amount of mechanical torque coming in, such that it equals the new electrical value, and the frequency will go back to 60 hertz where it'll return to the equilibrium. So the equilibrium point won't be a different frequency. It will always be 60 hertz because the control algorithm will essentially, that'll be one of its objectives. But the new values of tau M and tau E will be higher or lower than they were before. Okay, so now what we're going to do we're going to introduce the concept of an infinite bus. Have I discussed that yet in this class, what an infinite bus is? Okay, so an infinite bus is really it's a bus or a node that can supply or absorb an infinite amount of power and maintain a constant voltage, okay? So really, it's just, for our purposes, when we draw in the circuit, it's just going to be a voltage source, okay? But for a power system, it has a deeper meaning because it can be used to represent very large sections of a network or a power system on which I'm going to put R, meaning the thing that we're working with right now. R component has little to no effect. So we often think of the socket in the wall as being an infinite bus, okay, at least for the range of loads that we're working with. In reality, if I plug in even a very small load into this socket, somewhere along the line there's an element that's going to compensate for that small increased amount of load. Okay, the voltage will change ever so slightly, frequency will change ever so slightly, even if it's only for a fraction of a second. But for our purposes, for all intents and purposes, we can plug in anything up until the limit, which is the 15 amp limit, and it has no effect. It can be seen as an infinite bus. And the reason being, because the rest of the system is very large, okay? It has a very high moment of inertia, if you think about it in mechanical terms, right? So plugging in something relatively small, it's like the equivalent of me sticking, a twig into the wheel of like a Corvette flying along the highway. I mean, it has no effect. That moment of inertia is so large. So what we can do is we can use the infinite bus as a test case for looking at the way a synchronous machine works. We have this one synchronous machine, which is not so large, okay, that it has a significant effect on the rest of the system. And so we'll think of that rest of the system as the infinite bus. So our circuit will look like this right here. We'll have and this circuit should look familiar. It's the one that we just defined a second ago. We have our EAF, which again represents the interaction between the rotor and the stator. We have our synchronous reactance. Okay, which in this example they're going to call the internal reactance. Again, it's the same thing. We're going to be neglecting the stator, the internal resistance of the stator windings for this, so RS is equal to 0. So this is a really simplified version of that circuit that we drew up above. This right here is going to be our terminal voltage, right? And we're going to connect that to an infinite bus, which is simply going to be a value V infinity as shown. Okay, normally for infinite buses, we assume that the angle is 0, and that's the reference for the system. Yeah?
How can we drop RS?
Well, it's a lot like how we neglect the internal resistance of transformers. We neglect the internal resistance of inductors, right? When we put an inductor into a circuit, we say it's just J omega L, right? In reality, that's still a coiled wire, so there should be an internal resistance. Anyway, it's a small value, so it doesn't have much of an effect in the way that the circuit operates.
So it's just small relative to the scale of the other components?
Yes, yes. And we'll see that in a lot of power system problems. For almost anything except longer transmission lines, the resistance is often dropped. Well, obviously, for loads, we don't drop it, because for loads, the resistance value is going to be small, or corresponding to a relatively large load. They'll be drawing a lot of power. So the main resistances you'll see in a power system or in a circuit model that we're going to be looking at, resistances representing the loads, and resistances representing very long transmission lines. Often the internal resistance of transformers is neglected, internal resistance of the synchronous machines is going to be neglected, just like you said, because it's not having much of an effect on the answer. Okay, so we're assuming that the reference with respect for angle for this system is the infinite bus, which means that EAF will have an angle which we'll call delta. And so delta represents the phase shift between the generator and the infinite bus. So the reason why they call it XT here versus XS is because, and again, it depends on how the problem is defined, they could include other reactances in that, inside of there. Let's say that there's a small transmission line component right here. Anyway, they've grouped a couple other values into the reactance that we have right now. So I shouldn't say equals to, I'll say approximately equals to. Okay, so now, with this simplified model, we can define the three-phase power that's being generated by the machine. And then once we define that, we can begin to take a look at how and when we're going to begin to lose stability. Okay. So, let me name a couple things up here. So this is going to be IA. Okay, and we're also going to define a value that's called S infinite bus, which I have room to draw. You know what, I can draw like this. That's the power being absorbed by the infinite bus, which, as you'll see, is equivalent to the power being generated by the synchronous machine including whatever, accounting for whatever other inductances are looped into XT. Okay. So, we'll start with the most basic definition and then we'll keep building upon it. The most basic definition of S infinite bus is S equals VI conjugate, right? That's the starting point. So S will be equal to V infinite bus with an angle of 0 degrees times as you can imagine, right, that part of it is going to go away because right, the 0 degrees is not going to. That'll be added to whatever the angle of IA is, and so that will. Have it like that. So now, what is IA? IA, if we use KVL and look at what's up here, it'll be EAF minus V infinite divided by the JXT, right? EAF minus V infinite over JXT. And we can take this and plug that in there. And so we'll have a longer equation, which will be magnitude of the infinite bus times EAF minus magnitude of V infinite bus, again, because the angle is 0, we don't have to worry about it, over JXT, and we can't forget that this all needs to be made into a conjugate. Okay, so now, and we want to keep working with that equation. So we're trying to simplify this or convert it into a form that we can use for the analysis that we want to perform, which is mainly looking at stability. Right? We want to be able to see when this thing loses stability. So we'll break it up into two different pieces. We know we have V infinite bus magnitude times EAF magnitude with an angle of delta. All of that over JXT. We can't forget though that we are taking the conjugate there, so that really will become negative delta. Right? That's because of the conjugate. So that's one chunk. Then we'll subtract from that V infinite magnitude squared over JXT. And we don't have to worry about taking any conjugate here, right, because it's a real value. the magnitude squared will be a real value, so there's no conjugate. And we continue to do what we're doing, which is working with this expression. And so the last thing we have is V infinite E A F, both of them the magnitudes. Then what we'll have is negative delta plus 90 degrees, right? Because that's going to be taking the angle. This is a xt with an angle of negative 90 degrees, right? So this minus the angle will be combined together. All this over the value of xt plus, or actually minus, v infinite squared with an angle of 90 degrees over xt. Okay, so this expression here represents the power supplied by the generator to the infinite bus using the assumptions we had above. Okay, so now what do we want to do with this? Okay, let's start off by looking at the real portion, and then we'll look at the imaginary portion of the reactive portion. So P infinite, which is simply equal to the real portion of S infinite, okay, will be equal to, so let's take a look at the pieces up above. So, moving backwards, will this have any real part? No, right, because the angle is 90 degrees, so that's not going to play any role in the real, because the cosine of the 90 degrees is going to be 0. This piece, however, will. So the real power will be equal to V infinite magnitude, EAF magnitude, divided by xt times cosine of negative delta plus 90 degrees. And what we'll see is that so why does this apply? Cosine of x is equal to cosine of negative x. Okay, so we flip the signs there, and instead of it being negative delta plus 90, it becomes delta minus 90. And then another trig identity tells us that cosine of a value minus 90 degrees is the same as sine of that value. So what we end up with is write this sine of delta. And if we want to calculate three-phase power, simply multiply by 3 times. Again, we're assuming that the operation is balanced. So P, 3-phase, infinite is simply going to be equal to 3 times P infinite, whatever we had above. Okay, so now let's plug in a couple of values or remind ourselves of some things that we had defined before. So if you remember, going all the way back to the first section of this, the magnitude of EAF is equal to KF, which again, these constants, they're not going to be defined into a literal problem. Because they are dependent on the parameters or the parameters of the machine, times BF maximum, the maximum flux density, and this is going to in turn be proportional to the field winding current, right? So what does this mean, right? Inside of the rotor, you have that single field winding, which is going to be excited with a DC current, right? If we don't supply a DC current on the field winding, there won't be any magnetic field generated, there won't be any flux linkage between the rotor and the stator, then the rotation won't be causing any change in the flux linkage, and we won't get any EMF induced on the terminals, right? So IF is key to making this thing work. And so when we look at the larger equation, what we'll see is that the 3-phase power, or the real power, is going to be proportional to EAF and is going to be proportional to IF. So the higher the field winding current, the more power, real power that we're going to be generating at the output. And lastly, one other thing we need to point out here, if you look at pictures from way back, this represents the rotor angle, not the whole thing, so delta represents the rotor angle. If you go back to those pictures from the beginning, check. Okay. So now, and this right here is equation 9, 11. Okay. So what can we learn from this equation? Two different things. One is that IF is held constant, then so is the BF, the maximum flux density, and then so is the magnitude of EAF. Generally, this is the case. So what we're saying there is that when the generator is operating, the control system or the operator or whatever body you want to use to represent whoever's applying IF, they're not playing around with IF as the generator is operating, right? It's not a value that's generally being increased and decreased. So for the purposes of our example right here, we can say, let's assume that IF is staying constant. Now we'll see later on that IF can be used in a control algorithm for a synchronous machine to affect reactive power output. And it's another way of essentially performing power factor correction is by manipulating the IF value. But for this right here, let's just say we're not trying to do any sort of power factor manipulation, and so that value is staying constant. If that stays constant, then we see, so assuming IF equals a constant, then the three-phase power or I should say three-phase real power, not apparent, is predominantly dependent on sign of delta. So the phase shift between this infinite bus that we're assuming, right, the terminals of the generator, and the internal EMF, okay, that EAF value, the phase difference between those two values is going to have the hugest effect on how much real power our machine is generating. And if you think about this in physical terms or practical terms, we know that if we're not changing the mechanical input, the power is being converted into some combination of real and reactive power. So the more real power we have being generated, the less reactive power, more or less, and vice versa. So not having much real power being generated is not a good thing. So okay, we're going to draw a graph now that's going to represent how this works. So give me 1 second to set up the axes. And this is also going to come back to the question that we've been asking about stability. And I have to make it kind of big because there's a lot of stuff we're going to try to label. Okay, x-axis is our delta value. Y-axis is our P3 phase value of the infinite bus. Okay, now, right, we know that the relationship between the two of them is going to look like a sine wave, right? Because we said that P3 phase is proportional or is proportional to sine of delta. So all we really have to do is to draw a sine wave to begin with. So okay, so this right here is going to represent negative 90 degrees. This right here is going to represent positive 90 degrees. But our delta, the phase shift between the infinite bus and the internal EMF of the generator, which is 90 degrees. And so sine wave reaches a maximum at 90 degrees. And reaches a minimum at negative 90 degrees. So what are the different modes of operation that we're going to have? So first things first, on this side, we have generator type behavior. The amount of power being generated is greater than 0. On this side over here, right, we have motor type of behavior. The amount of power being consumed is greater than 0. Now, okay, so this whole region right here this is the region of stability. So in here, stability, out here, smile, frown faces for everybody who's trying to use their dishwashers. So if the magnitude of the phase shift between the EAF, so between the generator and the infinite bus is greater than 90 degrees in either direction, then we are going to begin to lose stability, or we're going to reach an unstable condition. Now, that seems pretty wide, and it is. So this is the maximum of the region of stability, okay, for this case that we have set up right here. The region of stability can be smaller as we start to take away some of the assumptions that we've laid out here. The fact that there's an infinite bus attached to it directly. Playing around with whether there's an internal resistance or not. But, et cetera, et cetera. We'll get into some of those later on. So, in a physical system, you're not going to see too many times where phase differences between adjacent buses are going to reach anything more than a couple of degrees. Okay, you're not going to see 50-degree differences between the two. If you see 50-degree difference, 99% of the time that already indicates you're well into an instability and things are on essentially crashed. You're not going to be able to recover without restarting the system. Yes.
In the beginning of the lecture, or of this lecture, you were talking about how this is a blackout. What's the difference between the blackout and the brownout?
Well, so a brownout is essentially when we run the system at a stable, in a stable manner, but at rated values lower than what we normally do. So it's essentially voltage droop and lowered current maximum from the plugs. So everything's stable, but you're not getting 120, you're getting 110 or 105, and the maximum current that you can draw, well, I guess that's predominantly set by the breaker, so that probably wouldn't change. But it's like your car is still running, but you're stuck in like first gear or second gear. Whereas instability is like your engine's exploded. Brownout also is a general-ish type of term that can be used to describe different conditions, but normally it's something that drooping voltage, reduced power output at certain nodes. Okay, so section 9.4.1 dives a little bit more into the steady state stability limit. And again, I know I've said this several times, hopefully you can see how this chapter is moving in a little bit more in an interesting direction. Now we can relate stability back to that circuit that we defined, and we can relate that circuit back to the values that are physically within the stator and the rotor themselves, and so you can see how everything sort of ties together. My hand needs a break. 30-second break. How was everyone's spring break?
Good.
Good? Anyone do anything really interesting? Just nods, but no details.
Well, to the Poconos.
Okay, nice. Is the weather good?
Yep.
Good stuff.
Poconos go.
Nice. What part? I did that once in college. You shouldn't shake your head. It's a rite of passage. You know, sleep in very dirty hotels. The hotel, when we went to Cancun, the hotel that I stayed in was so dirty. We asked for a wake-up call, and I didn't realize the next morning there was no phone, so someone would yell up the elevator shaft. Hey, like 12:32, like wake up, it's whatever time. It was an interesting experience, but I definitely got close to catching like a staph infection several times. Very, very, at least where I stayed. You hopefully stayed in a much nicer place. Good, that's a good thing. I'm pretty sure the place, I went to Cancun one time after that. For my honeymoon, we went to like a resort that was near Cancun, but just for fun we drove through, and I think they tore that place down. Or it collapsed, I'm not sure. Probably collapsed. All right, so, figure 911B, which I don't know. That's the figure I just drew. Okay, so, So if you look at this picture right here, you see that, right, there's a relationship. We can get more power up until a certain point from our generator, but once we go past the maximum value, which is at delta equals 90, then the power starts to go back down, and we can't get any more power. And actually, to talk about in practical terms, which I should probably write a note here. So why do we begin to lose stability here? It actually makes sense in practical terms, because what's keeping the system stable is that we move further and further to the right. We need to generate more and more power in order to maintain a balance between the load and the generator. But once we reach the maximum, it's like, imagine if you had a car where you push the pedal to halfway and the car speeds up, and then once you get past halfway, the more you push the pedal, the car begins to slow down. So that's essentially what's happening right here, is that the instability is because you've reached the maximum of what, for this given condition, meaning that you're not playing around with the IF value, you reach the maximum of what that generator can put out, and so the more you push the gas pedal, right, you're only making the situation worse by making the difference between the load and the generated generated power and the required load wider and wider, making that gap even wider. Okay, so what happens if we want more? Okay. Well, actually, we haven't gotten to the unstable. We're still in the unstable part. Okay, so we're in the stable region right now. We haven't talked about to do in other cases. So if there's no loss within the generator, which is an okay assumption for what we're doing right now, and that's the reason also why we've neglected the internal stator resistance, because that would be a loss value, or one component of the loss. If assuming no loss, PM is equal to PE. And so I'm sure you can sort of take the next leap from there, which is if we want to increase the amount of power that's being generated. So you might say, well, if I want to increase the power generated, why don't I just change delta? Okay, but you can't manually control delta. Delta is the phase difference between the infinite bus and the internal EMF of the generator. That's not like a dial that you can just turn up and down. So what you're physically going to do is you're going to open up the throttle, let more steam into the turbine, increase the amount of heat coming in. That'll increase your PM value, and that will increase your P value. What you'll have happen is that the rotor will speed up for a short period of time. For the transient, and you'll reach your new steady state. So now, if we take a look at what actually happens when we increase the throttle, you can see why the delta value is changing. Because you're here, okay, you want to get more power out of the machine, so you increase the throttle, which will cause the frequency to speed up, which will then, for every instant that it's faster than 60 hertz, the delta will begin to move, right? Because the delta is essentially directly dependent on that. So it'll move until you reach your new steady state, then it'll return to 60 hertz, and then it'll stop. So the movement of the delta is physically related to the speeding up of the rotor during the transient period. Once the transient period is over and we're back to steady state, the frequency goes back to 60 hertz, but the delta doesn't necessarily go back to its original value. Because to go back to the original value, the rotor would have to slow down for as long as it sped up, right? And then that would essentially bring you back to the first equilibrium. So when you go from one equilibrium to another, from here to here, right, you go from one PM value and one PE value to another PM value, another PE value, different deltas, same rotational frequency, 60 hertz. Okay, and then the next section gets really into the nitty-gritty details of instability. It's not really a good point to introduce, and we're already at 9:15. So we'll go ahead and stop there. Like I said, today I'll be emailing out a homework assignment, I'll be emailing out the